In this video, we will try to understand permutation using another technique through recursion. So the question that permutation asks us is, if you have n objects, what are the number of ways you can order them? So the way I to think about this is, suppose you have some children who wants to stand in the line in the school assembly every morning, right? And there are n children in the classroom, and they are standing in the line every morning, right? So what are the number of ways they could stand, right? So for example, if you have three kids A, B and C, one possible way they could have stand in the line is maybe B is standing first, then C, then A, right? Another way is maybe A is standing first, C is standing next, and then B, right? So what are the total number of ways they could stand? So this time what we will do is, we will start with first kid A, and then we will extend it to two kids A and B, and then again extend it to three kids A, B and C. Okay. So for the first kid, it's straightforward. There's only one way, like A stands. Okay. So when the second kid wants to join the line, and A is already standing in the line, so he'll have two options, right? Either he can stand before A, or he can join after A, right? So he'll have two options. So he can stand before A, which will be B and A, or he can stand after A, which is A and B, right? So for if there are like two kids, so there will be two possible ways they could stand in the line. So now, if the third kid C wants to join, so let's see what are all the options he will have. Okay, so these are the two possible ways the two kids already would have been standing. So when the third kids wants to join, he'll have three options, right? So he could stand just before B, after B, or after A, right? So he'll have three options. For this case, he'll have three options. So C could stand before A, after A, or after B. Right? So if we can write it down, so B and A are already standing in the line, so C wants to join, so C can stand before B, right? Or C can stand after B, B, C, A, or C can stand after A, right? So three possible ways. And then, so this is this case, right? And suppose A and B are standing, and then C wants to join again. So C can stand before A, or C can stand after A, or C can stand after B, right? So you can see that there will be six possible ways three kids can stand in the line, right? So what we can see is the pattern here, right? uh, so this is in fact 2 times 3, because there were two ways they could have already stood in the line, and for each of the way there are three options for the third person. Similarly, if three kids have already stood in the line, and the fourth kid, say D, wants to join the line, so they might be standing in one of these ways. So maybe either this or this, one of these ways, they would be standing in the line. So when person D wants to join, maybe for example, if this is the line they are already standing in the line. So so he'll have uh, four options, right? So he can stand here before C, after C, right, after A, or after B, right? So what we can see is for the fourth person, there'll be four possible options for each of this case, right? And we can do this for all these six possible arrangements. So we can extend this to something like this. Okay, so for the first person, there's only one person, there's one possible way, and for two persons, there's two ways, and for three, there are six, or like 2 times 3, and then for the fourth person, there are actually 2 times 3 times, and then we can see that for the fourth person there are like 4 for each of this way, right? So which is 2 times 3 times 4, right? Because he could join this line and he'll have four options, or he could join this line and he'll have four options, right? So that's why it will be 2 times 3 times 4. And we can extend this for the n kits. So for the n kits, it will be 2 times 3 times 4, uh, which will be n factorial. So this will be 4 factorial, 3 factorial, and so on. Okay, so we can also use induction to prove that this is n factorial. The number of ways you can arrange n objects is n factorial. So let's write that as s of n equal to n factorial. So we'll start with the base case. Base case s of 1 is equal to 1. As I said, there's only one child and there's only one way he could stand in the line, right? Next, what we have to do is we assume so it's true for some uh, kids k, right? So s of k, we assume it's true for some s k, which is s of k, and then we need to prove that s of k plus 1 is equal to k plus 1 factorial, right? So we saw that the base case is true, right? Let's prove that if it is true for if it is true for some number k, and if we can prove that if it is also true for k plus 1, then we would have proven for all possible n using induction, right? uh, okay, so the way we will do is we can use that s of k is k factorial, right? So what that means is you have like k children, and there is k factorial number of ways they can stand in the line. Okay, so let's suppose that this is one possible way they were standing in the line, right? For example, C1, C2, C3, and so on up to CK, right? This is one option, one way they could stand in the line. Or maybe C3, the child 3 is standing first, or then child 2, then child 1, and then last child k. So there'll be k factorial ways they can stand in the line, right? So this is k factorial ways, and this is what we are assuming, right? So what, and then we need to prove that if we can assume that we need to prove that this is true for k plus 1. So what happens is when k plus 1th child wants to join these one of these lines, he will have k plus 1 options. Okay, so he can stand here, he can stand here, he can stand here, and so on, or he can stand here, or he can stand here. So this will be k plus 1. Okay, so this will be k. Okay, for each of the existing ways, he'll have k plus one possible ways to join this line. So here this will be k plus one. So this, for this he can join in k plus one ways, and so on, right? So if you add them all, so it will, because there are already k factorial number of ways they could stand in the line, and then when the k plus 1th person comes, he'll have k factorial times k plus 1 ways that he could come and then stand in the line. And this is nothing but your k plus 1 factorial, and this is what we wanted to prove, which is s of k plus 1 is equal to k plus 1 factorial, right? So this proves that number of ways you can arrange n objects, or number of ways you can make n persons stand in a line, is n factorial.